This is alternative delivery for Math 2231 for 19th March 2020. A little bit of an administrative update. I'm still grading the limits thing, need to record those, but we will go over this in class. That is a coming attraction. Probably more immediately important is the quiz over derivatives is due next time. You will be self-grading it and self-reporting it, so make sure you have it done by next class. And I've established, because there will be some mark attained for it, it's now, I hope, appropriately incentivized. Today's topics are going to talk about the first derivative test, and I'll make some comments about inverse functions. I really encourage you to use the pause, rewind, and play buttons. You'll see those a lot, and that way you can actually get the full benefit of this lecture, even absent the interaction that we have. Okay, here's a couple of definitions that are important and we'll be talking about. A function is increasing if when x gets bigger, y gets bigger. A function is decreasing if when x gets bigger, y gets smaller. But if you think about the definition of the derivative, that means that we do have a way to know when a function is increasing and when it is decreasing. And so we can say that f is a continuous function and it's differentiable. Then if the derivative is positive for all x, the function's increasing. If the derivative is negative for all x, then f is decreasing. And whenever the derivative is equal to 0, the function is constant. Here is a picture that sort of illustrates that. The slope of the tangent line here would be certainly negative. The slope of the tangent line here would have a slope of 0, and the slope of the tangent line over here would be positive. So those are that's the results of those theorems and those definitions. So we have a problem. This says find the open intervals on which this function is increasing or decreasing. So what you want to do is pause this video, try to do it yourself, and then come back for the answer. Back for the answer. Okay, so f is differentiable on the entire real number line, so we need to find the critical numbers, because that's when it's going to be equal to 0 in this case. So when we take the derivative, we will get 3x squared minus 3x. We will factor that, of course, and we will find out that the critical numbers are x equal 0 and x equal 1. And because there are no points for which f prime does not exist, those are the only critical numbers. Now what we do is we do tests in intervals. This is why we reviewed this at the beginning of the term. So what we do is we consider the real number line, and we break it into 3 chunks. Those numbers that are less than 0, those numbers that are between 0 and 1, and those numbers that are between 1 and infinity. And we can pick test values in each of those subintervals to determine the SIGN of the derivative. So we can say x is minus 1, x is 1/2, and x is 2, for example. When we compute those, we find out where the function is increasing and decreasing. So it's increasing when on this interval from minus infinity rather to 0, and it's also increasing from 1 to infinity, and it's decreasing otherwise. The picture verifies that, and so that's one type of problem that you may encounter in your homeworks. And the guidelines are you do exactly what we said. What you do to find the intervals where it's increasing or decreasing, you find the critical numbers and use these numbers to determine test intervals. It breaks the number line into a bunch of pieces. Determine the SIGN of f prime of x for at least one test value in each of the intervals. And then determine, based on the sign, if it is positive, it is increasing, if it is negative, it is decreasing. And those guidelines are valid not only on a finite interval, but on an infinite interval, which is the one we just looked at. We have some more definitions. A function is called strictly monotonic. Monotone, for example, means I'm speaking in the same tone all the time, and so monotonic means same direction, same rate of change on an interval if it is either increasing or decreasing on the entire interval. Okay, so for example, this one is increasing on the entire real number line. Students should note that a strictly monotonic function, if it is differentiable, has a derivative that never changes sign, S-I-G-N. This is something that is important for you to realize as you go forward, especially in higher calculus things. Students should also note that a strictly monotonic function is of necessity one-to-one, because if it's one-to-one, it never goes back and has the same value for y again. So what can happen is a student, and we're going to do this later in the period, if you want to show something as one-to-one, if you show the derivative never changes SIGN, you're finished and you know that it is one-to-one. And looking ahead to Calculus 2, the easiest way to determine if a sequence is increasing or decreasing is often by considering, I'm putting this in quotes because this has to be interpreted correctly, but the derivative of the associated function with the sequence is always positive or always negative. I now have a story. I'll tell you this story quickly, but the reason I'm telling you this story is that students have told me, good students have told me, this story was useful for them. So once upon a time, I wanted to buy a car. And my wife didn't like the car, and I asked her why she didn't like the car. And she said it has crank windows instead of power windows. Now, I bought her a car that had power windows, so she was just fine, and she almost never rode in my car. But anyway, it had crank windows. One day, I was driving her car back from Indiana. She loved her parents, and we always visited them, and we would always stay late at night, so I was driving back. It was pouring down rain. We were driving her car, and everybody in the car was asleep. I was listening to a country music station at the time. This was in the days before iPass, so I pulled into the lane to give the toll taker my money, and I used her power windows, put the window down, gave them my money, and then I pulled out. But then I pressed the button to have the power windows go up. Nothing happened. I got wet, and there was no one to complain to because everybody else was asleep in the car. Anyway, I went home and told my wife when I woke her up for her to go to bed. I said, "Hey, your power window is broken." She says, "You better fix that tomorrow, first thing." So tomorrow I went, and the mechanic told me, "Oh my God, that's really going to cost you." And I said, "Why?" And he said, "The part is very expensive, but also it's a bitch to get to. And so it's going to be a lot of labor too." So I repaired it. So what does this mean looking forward? Well, crank windows always work. Power windows are really nice when they work, but they don't always work. And when they fail, it's really bad. I got very wet on the way home. Now, the thing to remember looking forward is the first derivative test is like crank windows in a car. It always works. The next lecture, we're going to talk about the second derivative test. That's a coming attraction, but it's like power windows in a car. It is very nice when it works, but it can fail. And like power windows, it can fail spectacularly. So here is Jim's picture of the first derivative test. We'll look at a description of this later, but here the CI's, C1, C2, and C3 are critical numbers. So there's a critical number, there's a critical number, and there's a critical number. So first step is you find the critical numbers. Then what we do is we say what's happening with the derivative on either side of these critical numbers. Remember, the derivative might not exist at these critical numbers. So over here you see the derivative is negative, the slope of the tangent line. Over here the derivative is positive, and that has to be, look at the picture, a relative min. Over here, the derivative here, the slope of the tangent lines are positive, the slopes of the tangent lines over here are negative, and that has to be a relative max. Now I can have this kind of thing where the slope of the tangent line is negative here and negative there. or here it can be positive here and positive here. But if the SIGN of the first derivative does not change, it is neither a relative max nor a relative min. I want to stress that this is a definitive conclusion. Here you know that you have a relative min if you have this situation. Here you know you have a relative max if you have this situation. And here you definitely know that it is not a relative max nor a relative min. The test never fails. I don't memorize the statement of this theorem. I draw this picture every time I am confronted with a problem. But there is a statement of the theorem here. And so this talks about it. So if c is a critical number of a function that's continuous on an interval containing c, and if f is differentiable on that interval except possibly at c, then you can classify f of c in the following way. If f prime changes from negative to positive, it's a relative minimum at these ordered pairs. If it changes from positive to negative at c, it's a relative max. And if it's either positive on both sides or negative on both sides, then it's neither a relative max or a min. These pictures are better versions of the same thing that I talked about with my picture. It always works. Okay, so let's look at a problem. We're supposed to find the relative extrema of this function in the interval 0 to 2 pi, and we want to use the first derivative test to classify the critical numbers. I'm going to suggest you pause this and try to work it before continuing. Let's continue. Okay, so since f is continuous on that, we're just noting that f is continuous on this, so we're going to find the critical number. So we'll take the first derivative, and when we take the first derivative, you ought to be really good at this now. This is 1/2 minus cosine x is equal to 0. We're going to set that equal to 0, which means we're solving this equation, and we will get this as critical numbers. Now you might say, oh, there's a whole bunch of places where that happens, but not in this interval. These are the only two places in this interval. Yes, you do have to solve trig functions. Because there are no points for which f prime does not exist, you can conclude that these two are the only critical numbers. And so then we'll do test points. So we draw a real number line, mark those on the test points. So we're breaking the real number line into three pieces. This piece, and this piece. We find test values in each of these intervals. We evaluate the SIGN of the first derivative everywhere, and we know that it is decreasing, increasing, and then decreasing. Now, if we use the first derivative test, then we know from looking at these conditions that this is a x value where a relative minimum occurs, and there's a relative max at a point where this x is equal to 5 pi over 3. A good example. And the picture verifies that we did a good job with that. Here's another one. Find the relative extrema of this, and what we need to do is use the first derivative test. So I encourage you to pause and then hit rewind and play. Okay, we're back again. Okay, again note that f is continuous on the entire real number line. And now we have to take the derivative. Now when we take the derivative, we use this rule, and simplifying is good. So it's going to be 2/3 this business to the, that's going to be minus 1/3, and the chain rule is going to be, that is going to be times 2x. If you simplify it, you get this expression. Now, this expression is 0 when x is equal to 0, and does not exist when the denominator is equal to 0 or x is equal to plus or minus 2. So the critical numbers are x equal minus 2, x equals 0, and x equal 2. And so we divide the real number line into intervals, and we take test values from each of those intervals and evaluate the SIGN of the first derivative in each of those sub-intervals. So if we apply the first derivative test, we can conclude that f has a relative minimum at the point -2, and if we put -2 in there, that is -2, 0. I usually will ask you for both the x and y coordinates. We have a relative maximum at the point 0, and that's the cube root of 16. Now some students might say that's the ugliest damn number they've ever seen in their life, but there are no ugly numbers. And another minimum at the point 2, 0. Now there is a picture of this, and it confirms what we talked about. And note that these critical values that we have ended up being the relative mins. That's the relative max, but these are places where the first derivative did not exist. Okay, one more example. When using the first derivative test, be sure you consider the domain of the function. As you'll see in this example, knowing about the domain influences the function. So again, pause and hit play when you're ready to resume. Picture of this. Apparently I don't. Sorry about that, but the picture will confirm that. Okay, this is a problem where you get to be an engineer. We're talking about the path of projectile propelled at an angle theta is given by this. This is kind of a physics or engineering thing, and in your physics and engineering classes you might derive that. But my question is, and here's some values for g, v0, and h. At what value of theta will produce a maximum horizontal distance? You can pause, rewind, and play. Well, what we need to do is we're going to find out what is the distance. Now, when we solve that, we're going to get, because x is the horizontal distance and this was the vertical distance, so you're going to set that equal to 0. That's where it will hit the ground. Y equals 0. So when you solve this, what you will get is that these are the two values for x. And so if we simplify this quadratic expression when x is bigger than 0, we'll find that x is equal to cosine theta and this expression. Now you can apply the first derivative test here. Now it turns out that this is tedious, but it is instructive. Doing the hard work could play some labor, but in this case we're being engineers and we're just saying we can use some technology to solve this, and if you do, you'll find out that theta is approximately just short of being 2/3 of a radian, or 35 degrees. And if you were to graph that, you'd see that that actually does maximize the range. That's the biggest x value that you find. So for this set of parameters, 35 degrees is the one that you want to shoot at. This is a very real engineering problem. Now I'm going to pause here and call this version 1, or part 1, and I am going to give you a part 2 because there's something I need to add from a previous discussion. So there will be a part 2, but dig into part 1.